Hello, Vikings. Today we're going to be talking about Newton's first law. Our objectives today are to look at balanced and unbalanced forces. We're going to look and talk a little bit about friction. There are 3 types. And we're also going to talk about what inertia is. Okay, so first we're going to look at force. Force is simply a push or a pull. And when we have a push or a pull, it can change an object's motion. It doesn't always do so, but often it does. So if you have a student sitting in a desk and another student was joking around with them and they came by and pushed them, the student could fall out of the chair, or if it was a really light tap, may not move at all. So a push or a pull is called a force. So how do we measure force? Our units, when we talk about force, is going to be in newtons. And a newton is equal to a kilogram meter per second square. So when we have more than one force acting on an object, we will try to find out what the net force is. And that's considering all the forces acting on the object. So here's an example of trying to calculate a net force. We have 2 young men who are trying to push a canoe into a stream, and they're both going in the same direction. The guy who's in the front is pushing with 70 newtons of force. The young man in the rear is pushing with 90 newtons. So the net force of the 2 gentlemen would be 160 newtons. We're going to add them because they're going in the same direction. So you're pushing with a total net force of 160 newtons in this example. All right, so we have 2 kinds of forces, or 2 ways that we classify them, often as balanced or unbalanced force. And when we look at a balanced force, you're not going to have any change in motion because the forces are equal and opposite in direction. So here's an example below. I have some people who are playing tug of war. They're both pulling with 500 newtons in both directions. So even though you have 2 different forces acting on the rope is not moving because it is balanced. So the net force in this instance, 500 minus 500, is 0. There's no movement. But that rarely happens when you're playing tug of war. More often the rope is moving in one direction, right? That's the whole goal. So when you have forces that are not equal and opposite in direction, you're going to have some movement. So again, I have an illustration of students who are playing tug of war. In this instance, you've got Brian and Alyssa who are pulling with 10 newtons of force, and Daniel and Maria with 12. So in this example, what you're going to find is the rope is going to move to the right, of course, because they're pulling with more force. And the net force in this instance is going to be 12 minus the 10. And so you're moving 2 newtons to the right. So if we're going in the same direction, we're adding. But if we're going in different directions, we're subtracting. So Newton's first law is that, and you've heard this many times in your education, and you may have heard it in put into different terms, but usually we hear it described as an object in motion will stay in motion, or an object at rest tends to stay at rest. And it's basically just saying that if an object's still or if it's in motion, it's going to stay in whichever state it is until something else acts upon it. Okay? So just like this example where you've got someone who's about to flick the piece of paper out from the quarter, everything's going to stay right where it is until the person who's ready to flick, until that moment when they flick that paper, nothing's going to happen to the objects involved. Newton's first law is also called the law of inertia, and that's because inertia is the tendency of an object to resist that change in motion. And we see it most frequently, a good example is in auto accidents, or even just when you slam on the brakes in your car. You are traveling with your car when you are riding in it at the same speed that the car is traveling. So the reason you go forward when you slam on the brakes or you were to hit another object is simply because you're going to stay in motion until something stops you. And if you've hit, like, let's say a car hits a tree, the car has stopped, but you still haven't stopped. So you're going to keep going unless that seatbelt catches you. Also important to know with inertia that it's affected by the mass of the object. So if you have someone who's in a car that has more mass, like let's just say an adult versus a child, it's going to take a lot more to slow down the adult than it does to slow down the child, because the adult has more inertia. Okay, so aside from forces that act upon an object, there are three other things that can change motion, and they are friction, air resistance, and gravity. And you're probably familiar with these. We'll learn a little bit more depth about the ways that friction can be impacted, air resistance can be impacted by different things, and we'll learn all the little factors that come into play when an object is moving. So the first one we're going to look at, and we're just going to define the three first before we go into specifics. The first one is friction, and friction is a resistance to motion simply because objects are touching each other. Okay, so if we have a book sitting on a counter, there's friction there simply because the book is touching the counter. Air resistance is resistance because an object is traveling through air, and that air is going to slow it down. So that's why when you have these people jump out of airplanes, before they're putting on their parachute, that the wind is really, and the air is really buffeting them as they fall. So air resistance will impact motion. Gravity is another thing that will impact, and gravity is the attraction that objects have to one another. Alrighty, so let's go specifically into friction. Today we'll notice that most things have threes. There are three types of friction, and these are fairly simple to learn. We have static friction, and this is simply the friction between surfaces that aren't moving. So a good example of static friction was the reference I made just a few minutes ago to a book sitting on a counter. Neither object is moving, but there is static friction between them. And if I were to take a book that is on the counter and start sliding it across the counter with my finger, you'd have something called sliding friction. Okay, and that's present when you have two objects moving past each other. The last one is rolling. We see that with anything that has wheels, cars, skateboards, and as in the picture, roller skates, and this is just friction caused by rolling objects. Okay, so those are the three different types. There are also three factors that affect friction. All right, the first one is surface type. Okay, if you've ever played with Hot Wheels cars and you make a little ramp out of the track, you know that the cars will go down pretty quickly. Now, if you were to put some sandpaper and line the track with sandpaper, the cars are not going to move as easily, and that's because you've got greater friction. Okay, also the amount of force. If I was in the classroom and I am trying to slide a chair across the classroom floor, it will be a lot easier to slide the chair if it's empty than if I had a student sitting in it and was trying to push the student and the chair, because there is more force, the student's pushing on the chair down, and it makes it more difficult. Okay, and also surface area. You're going to have more friction if your surface area is larger. That means you have more contact. Okay. All right. So we also have 3 factors that can affect air resistance. And the first one is speed. And a good example for this is if you've ever been riding down the road and you roll down the window and you stick your arm out the window. If you're going very slow, you don't have or feel a lot of resistance. But once your car gets to the 50s or 60, you'll start noticing it's harder to keep your arm still and straight because you have greater resistance of the air hitting it. Also, the larger an object, the greater the air resistance you're going to have. And that's made clear if we were trying to pilot a plane. It would be a lot easier to get a small Cessna into the air versus trying to get a 747, because 747 is so much bigger. It has a lot more air resistance. The last one, shape, can affect air resistance. And a really good example of this would be comparing the speed of fall to the ground of a piece of paper that's flat or a piece of notebook paper that's balled up into a really tight ball. If you were to take both of them, the balled up paper and flat sheet of notebook paper, and drop them from shoulder height, they are not going to fall at the same acceleration simply because of air resistance. It's going to take the flat sheet of paper longer to get to the ground, simply because it does have more resistance. Okay, so we've done 3s all day. We've got to have a 2. What 2 factors affect gravity? Mass. Okay, so the bigger you are, the more attraction, and also distance. Much of the same way as if we're playing around with magnets, you know that the closer magnets get together, the easier it is for them to attract. It's the same way with gravity. The closer the 2 objects are, the greater the attraction that's going to occur. All right, so we also have something called the law of universal gravitation, that any 2 masses exert an attractive force on each other. Okay, and you will notice during the semester that we will have a lot of laws. Okay, next we're going to look at the acceleration rate of gravity, and it is 9.8 meters per second squared. This is a number that you need to learn because we're going to use it in some of our calculations as we go forward. And one thing to keep in mind, that this acceleration is only true if you ignore air resistance. Because as we talked about earlier, if you do drop a piece of paper that's balled up versus a flat sheet of paper, they're going to appear, or they are going to fall at different rates. And the reason is because of that air resistance. I usually have students do a little exercise in class where they take a tennis ball and they ball up a sheet of paper to make it just as close to the same size as the tennis ball as they can. And what happens is when you drop the 2, even though the tennis ball has a much greater mass, they both fall at the same rate because the air resistance is virtually the same. All right, and the last thing we want to cover today is terminal velocity. If you fall out of a plane and you're accelerating, there's a point where your the rate of gravity and air resistance become balanced. So your net force is 0 and you're not going to accelerate any faster. So there's a point where, whew, that's the fastest you can go. And I have never jumped out of a plane, nor do I hope to, but it appears like when I watch the videos that it's really fast. So anyway, that's it for Newton's first law today. I hope you have a wonderful afternoon.